Hello and welcome to this video. My name is Robin Mitchell and today Electropages is here at Avnet Silica. In this video we're going to be talking about heat pumps.
Yes.
And heat pumps are quite interesting, I think, because there's something that there's still, they've been around for a while, but it's only recently, I'd say, that they've really started to pick up interest in different markets, commercial, industrial, all those different areas. So I think the first question I'd like to ask you is, what's the current state of heat pumps and where do you see them mostly being used?
The current state is that they have a motor inverter in there that drives the compressor, and basically it switches on and off and does some kind of very limited power control. And mostly they're used, the biggest use case for them is like residential housing for private households to kind of heat either one or two houses. It depends if it's detached house, just one. If it's semi-attached or something, it's then like heating two houses or more.
And I suppose my first question about heat pumps then on that residential sort of area, in terms of like their capability, whenever I'm trying to compare them to electric heating or maybe gas heating, how do they actually fare in terms of efficiency per, let's say, like in terms of the cost of actually heating or cooling a home? Because I think heat pumps do both, don't they? They can both heat and cool because they're reversible mostly. Yep. So in terms of efficiency compared to a typical heater, how do they look?
So you can imagine a heat pump as something as a heat exchanger. So you put electrical power in and you get some heat power out, and usually over the full season we're looking at the conversion rate of 4. So for every kilowatt of electric power you get in, you get 4 kilowatts of heat out of it.
And so essentially that electric power is kind of like being used to essentially steal the heat from the outside air or the ground, wherever it is, and which makes that side cooler, essentially bringing the heat in using your evaporative cooling stages, and then that's then being used to heat the inside. And so, so when you say so this is where the coefficient of performance comes in, these kind of numbers. And when you say 4, you're saying for every 1 unit 4 comes out. So does that actually mean that compared to a 1 kilowatt heater, let's say, it would actually give you 4 kilowatts of heating?
Yes.
And so it really does actually make it 4 times more effective than a standard electric radiator.
On average. So
on average. Okay.
You always need to take into account, we're here in the UK now where the winter is not that cold as, let's say, in the Alpine areas. So if you have like minus 10 degrees C outside, it's obviously less efficient because the temperature difference it needs to
the greater the difference,
the less efficient they are. So that you always need to take into account. And so overall, or let's say from like January to end of December, you get an efficiency average about 4. So it's the
so sometimes it'll go up, sometimes it'll go down, but on average it's about that sort of thing. And that's when you and that only matters on that average because typically you'll keep your house in the same state. And so it doesn't matter if you're paying more to keep it in this state here than there, it's always comfortable. And so therefore overall you've only paid X amount of energy to sort of make it work. So in places like the UK, I'm guessing heat pumps tend to use the air as their sort of heat medium, which they're taking the energy from. But in cooler countries, would you use maybe like ground pipes or something like that?
It would make more sense because then it's more efficient because the temperature difference is not that high. But you always need to take into account if you got like a air heat pump, it's always the cheapest option. And often it's the cheapest option is kind of not the most efficient one, but still it pays off because you don't need to hire someone going with the digger.
Oh, exactly. And then if it goes wrong, you can easily service it. It's not dependent on some underground system, like you say. And if something goes wrong there, that's going to be a really expensive operation. So that does make sense. So heat pumps, they're slowly becoming popular. But I suppose with such efficiencies, why are they not more popular than they should be, considering how efficient they are?
The other options were cheaper in the past. So in 4 years ago, when you did a quotation on a heat pump and a gas-powered house heating, the heat pump, the whole system was at 7K euros. Gas heater, 3K. So it's a no-brainer that you pick the gas heater. But now the situation changed a bit through the gas price surge, I would call it. People are more looking after, okay, what am I doing for heating the house? Because you need to have your house heated. And so a combination of heat pump and solar on the roof really makes sense, because then you can power the heat pump and you're more independent on your energy usage, and it does not really affect you that much when you kind of...
That's interesting, isn't it? So like you say, with a heat pump, the energy you're providing into the system, it's not heating, it's moving heat from, or essentially moving energy from one place to another. That's a bit like a motor pushing water from one area to another. Yeah. And what's interesting is that when you use solar power, even during the middle of winter, it only needs to be enough, because you're so take each like sort of square meter of land. Typically, it's about 1,000 watts per square meter from solar. You know, in terms of, and that depends where you are on the planet. I mean, the further north you go, the less it's going to be. But you're not using that energy to heat; you're using that energy to drive the system. And because you've already got that energy in the atmosphere, if it's an air-cooled one or an air-heated one, depending which way it's going, you don't need that many panels to make that thing work, which is quite interesting. I never really thought about it like that.
And so to be fair, when you're going through the winter with the heating, the disadvantage of the whole system is in summer you have peak power with your solar panels, and in winter you need to peak heating.
That's when you need.
Yeah, and that's a bit the disadvantage. But you can kind of leverage that effect with feeding into the grid. You get paid for feeding in your electricity, and then later that year just take it out again. So it's not kind of fully covering, but sort of. Yeah. Because you always have a lower feed-in tariff than kind of purchasing tariff. That's always the thing. And normally you don't like have enough power from the PV system to heat your house in December or January.
So with heat pumps obviously coming on the rise, and they're good. I mean, I think if I remember correctly, there might be some regulations coming into the UK where every new house needs to have one, or certainly in the next 10 years they'll certainly need to have one, because I know people are moving away from gas and other sort of fossil fuel derived heating. So that means there's going to be a lot of these systems manufactured and developed and deployed. So what would you say is the biggest, let's say the biggest challenge that they're currently facing in terms of integration with silicon? Because obviously Avnet Silica, you guys are going to be there providing engineers who need to build these things with all the silicon devices they need. What's the biggest challenge you can foresee?
There's a new regulation in place. I don't know the exact name, unfortunately, but when you switch on the compressor, you have a big inrush current.
Is this a regulation in the UK, EU, or both? Sorry.
EU. Okay. So what this regulation does is take stress off the grid, because when you switch on the compressor, it has a big surge in power, and then it kind of runs smoothly. And so they need a soft start where they need to apply software algorithms in the inverter just to make this happen. Yeah. And then you also, with this software algorithm and the power electronics behind, you need to ensure a longer lifetime of the compressors, because for if you talk to one of these companies making heat pumps, they're expecting their heat pumps to live 21 year plus onwards, and so no experiments there. So you need to really be sure that this thing works for a really, really long time. And so this is a lot of complexity, and you also have then EMC complexity then with all the inverters, and you need to have a power factor correction and stuff like this. So instead of just switching something on that's a motor on a three-phase system, you do have more complexity.
And that's because the power going to these systems will be single phase. There will be
lots of them single phase. So 6 to 8, 6 kilowatt ones will stay single phase above. Like it always depends on what steps these manufacturers take. But a 10 kilowatt is very likely to be three phase.
And so when you say 6 kilowatt, are you saying that there are heat pumps there that sort of go up to that power rating? But
the heat power rating goes to 6 kilowatt.
But the motor power is going to be more like 2 or 1?
2, 3.
2 or 3, yeah, because it's got that coefficient of performance multiplier. So yeah, that makes sense. So you'd be putting a kilowatt or 2 kilowatts.
If you read the data sheets of this heat pump, it's always the heat output power it can produce.
Okay, I see.
So it's not the input.
But that's still a lot of power for a compressor to draw on a residential system, which is why I can understand that inrush current could be a serious issue. Because you look at devices like fridges, freezers, anything that currently has a compressor, they're nowhere near that kind of power level, nowhere near. So if every house starts sticking these, starts putting one of these heat pumps in, and then suddenly, it goes back to that problem we saw in the EV episode, whereby it's not that all the cars are going to be running on a megawatt, but it's the fact that the moment they start or the moment they're plugged in, you're going to get these huge inrush currents, and that's going to put stress on the power lines, stress on it, and stress on everybody else's homes, because that's going to have a knock-on effect on other residential areas. So in terms of silicon technologies, what do you think is going to become critical in heat pumps?
Critical. I don't see anything really being critical. I see for heat pumps a mix of technologies really. For the lower power end of heat pumps, to put it correctly, I see a PFC stage that can be made of silicon or GaN, because it makes sense. For the power stage itself, I would say it will stick with IGBT technology because of the inrush currents, the handling, and also the lifetime. Because when you switch fast, you stress the wire-to-wire insulation in the motor, and that's what you don't want to have.
And also the voltage level as well. We're not going up to 800 volts. We're sticking around 230, aren't we? Input, yeah.
If we're talking single phase, the DC link voltage will be around 420.
Oh, that's actually a good question. So these compressors wouldn't be directly powered off the mains. They would have a sort of like a. Would they be DC based? Would they be?
It's an AC motor that's in there, but you have a variable speed control in there.
Oh, of course, you need to sort of change it, put it through a transformer, and sort of modify it. That does make. Oh, okay, yeah, I see. And then that's why you got the power factor correction, because you've got to make that change, and so you've got to make sure that you're. That does make sense. I was about to say, because I would have thought it'd been very odd to have used a DC motor to sort of drive a compressor when you've got the AC there already.
I mean, if you want to, you can do it. I mean,
you could, and that's where these little silicon carbide technologies come in. But it would not make sense. I would say it would certainly be easier to use an AC system.
And for the three-phase higher power ends, I see certainly silicon carbide can take the job in the PFC, but still IGBTs on the compressor side.
But moving to three-phase, heat pumps are not just going to be residential. I can very much foresee them becoming more commercial as well.
There are big installations at supermarkets, shopping centres, malls and stuff like this.
And in those applications, that's where your three-phase comes in, because those compressors are going to be a lot bigger than the ones you use in a residential application.
They're enormous, yes.
Yeah. And so again, in those applications, that's where things like silicon carbide will then become important.
Yes.
And so how would it play a role in those applications? So if we just sort of break down the design of a typical heat pump, how does that come together, and where do you see different technologies being integrated into each section?
So the heat pumps can be constructed in various ways. So one popular thing at the moment is split mountings. You have the control system in the house and the actual heat pump outdoors with the motor and the motor inverter. So it's very compressed and dense space outdoors. New regulations make it necessary to keep the gas content in the heating circle low. So it's like all compressed in one device being outdoors. Yeah. And it's also, again, motor inverter, PFC, all very condensed, kind of in a small space at the motor itself. And if you do everything with IGBTs, it gets a decent size in material that you add to the motor. And if you're able to do, let's say, the PFC with silicon carbide and the motor inverter with IGBTs, it's a way smaller thing to kind of integrate into your mechanical system. And this makes more sense.
And what kind of sort of space reduction do you get as a result of using? Was it GaN? Sorry, was it? Or
for the single-phase GaN, for the three-phase silicon carbide.
Got it. So what kind of size reduction do we get for each of those technologies compared to IGBTs?
It always depends how you can leverage it from a magnetics point of view.
Always comes back to magnetics.
Yeah,
always does.
For magnetics, you have to use lit wires and sorts of stuff, so it's complicated. But from the magnetics, I think you can achieve up to like half the size.
Oh, blimey. And I take it that's going to be about half the weight as well, at least.
Yes,
depending on how it's designed.
The thing is, it's the ideal case. You never be able to achieve this, just to shrink them by half. And the other thing is the PCB will not be shrink by a factor of
It's only going to be wherever the inductor was, essentially. So it could be slightly smaller because that bit's gone.
Yeah.
But in terms of weight, I mean, let's be honest. Magnetics tend to be the heaviest part of a board by far. They can be really heavy.
Yes, but if it comes to a heat pump, you don't care. The
Because
compressor.
it's sat on the ground. It's not like it's in a vehicle or something.
Yeah.
That's where it becomes a big concern. So. Yeah, so weight, which is funny because weight's one of those constraints that doesn't actually matter. It's so
Here
much compared to maybe an EV.
It's this in the PFC stage here. It's not the weight that matters; it's more the efficiency you want to have. And it always depends. If you are really want to get the most efficiency out of it, you need to stick with wide band cap. If you say, well, it's not going to be my premium heat pump, I do sacrifice my efficiency here and there to make it more affordable, go with IGBTs, you're completely fine. So you just need to kind of be aware that you need to sacrifice on efficiency, on size, and that kind of stuff.
Well, yeah, like I said, any technology comes with its own pros and cons. There's no such thing as a technology that just does better than everything. Otherwise it would absolutely overtake. But on that note, actually, what kind of efficiency differences would we see then from an IGBT versus sort of a GaN/silicon carbide heat pump?
Ooh, that's a difficult question.
Difficult question. Depends on the design and the way it's integrated.
Yeah, but I don't want to give you that kind of broad answer.
It's too broad. Right? So it's going to be one of those application / sort of case by case thing. So you might find one application can get 90%, another one maybe only 87%, another one maybe 72%, depending on exactly how much power is being used. And so but of course there are going to be regulations that require a certain efficiency and require engineers to do the best they can. So because of that, how does Avnet Silica step in that design process of a heat pump?
Mostly either the heat pump company themselves or an EMS company that does the design for them comes to us and says, look, we need to design a new heat pump electronics, and then we help them ideally on all sides. So for me it's the power electronics. I try to guide them through the specifications and where to use what and maybe what to leave out because technically not feasible or price-wise not really there where they want to have it. And my colleagues then come in and say, look, this controller, this connectivity, this maybe cloud solution, whatsoever, and then we give them consultancy along the development process, and that's what we're trying to do and trying to offer them.
So when it comes to Avnet Silica sort of helping engineers in this design stage, it would be at the early stage where they're still coming up with the plans and the schematics. It wouldn't be sort of like halfway through.
No, and I always urge the customers to pull us in as early as possible, because the thing is, when they have, when I talk to them, I said, look, a half-decent specification is okay for us because we can work on that already. And if you have changes afterwards, the work we need to do sort of twice for you is okay for us. We want to have support there, and it's better to do like the work twice up front and not like 3-4 times.
Well, exactly, and I think it's also that the earlier you get involved as well, is that you might be able to identify issues before they even rise, because anyone designing any piece of equipment, especially on this sort of size, it's not going to be cheap. It's going to have a lot of design challenges. It's going to be a lot of sort of little bugs to figure out, and the more problems you can find at the very beginning, the less money it's going to cost you in the long run. And I think that's one of those things that tends to. I think that's one question I tend to see from engineers as well in the area of silicon carbide and GaN, which is that they tend to be a bit what's the word, shy of the price. Maybe would be the word I'd use. Maybe they're a bit nervous of the price. But I think you tend to find that when you integrate it properly, you probably find it's the same, if not cheaper. But could you elaborate a bit more on that?
The whole pricing thing is a bit of let's say, a commercial exercise, because if you compare an IGBT with the silicon carbide, it's always the silicon carbide that's going to be more expensive. But you save costs on other areas, and ideally the whole system cost is the same but more efficient, or even a less price tag. But it's a commercial exercise we need to do with engineering, purchasing, and our salespeople to make sure that this really sticks. So you can't just globally say, well, use silicon carbide and your whole system will be smaller, cheaper, more efficient, whatsoever. It's not true in every case. Sometimes there is this one little bit that makes it more expensive.
Yeah.
And equally efficient, and then it's like, okay, where is the point? And that's a more, let's say, resource intense thing to do, but at the end you have a clear picture and this paints off.
And so it's not just the parts that you're investing in, it's also the time, the engineering around it, learning how to use the parts, sourcing the correct gate drivers. That's, again, something we discussed before, is that unlike your typical IGBT or your silicon chip, transistor, silicon carbide and GaN, they need to have special gate drivers because of the way that they work. So it's just sort of like an extra step that's involved. So with all that considered, what would you say then would be the biggest drawback, or what would you say is kind of like the barrier of using these technologies in a heat pump that engineers are currently facing?
Just go from front to back. For the PFC stage, I would say the single phase with GaN, you need to be really careful with switching.
Yeah.
Because normally you do a totem pole PFC.
Right.
That does the job for you. You don't use the bridge rectifiers anymore. Yeah. So in theory, it's quite easy to do, but you need to be really aware when to switch and what, because the GaN transistors do not have an intrinsic body diode. They do have a reverse characteristic, but that's not really good. And
so any back EMF or anything like that, that's going to cause, it's just going to go right backwards.
No, if you just reverse the current, they have a reverse characteristic, but it's not like a diode that saturates at 1 voltage.
Oh, I see. Okay.
So it increases over current, quite unideal, I would say. And the GaN dies are really small, so they cannot take a lot of losses. And this is pure loss on the GaN die, which is not ideal. So you need to be really aware of the switching.
I see.
There's 2 analog PWM controllers at the moment in the market that can help you with that.
So just to make sure I understand this correctly, so with the typical sort of NMOS transistor, you have the body diode, which means if there's a reverse current, it'll go basically dump through that diode, and that's the body diode, which means it's kind of the whole of the silicon structure that will take that current flow. But in the case of GaN, because it doesn't have that, you're saying it's actually sort of like almost like the junction itself, which has to deal with that reverse.
The transistor itself has to deal with it. There's no body diode where it can kind of divert to.
Yeah. And so then that's why there's the danger, because if it's too large, it's going to potentially damage that. And I suppose it also increases the heat of the area as well, which also would affect the chemistry of the design as well. So I imagine it could cause issues with the gate and the drain and sources. Would it?
What do you mean by heat? I mean, it's all.
So you'd have like you'd have an intense amount of heat in that gate channel, wouldn't you? I imagine.
In the whole device, really. So
it's really the whole device.
So you have the gate, then you have the gate oxide, and the heat is produced
around there, and so and so but that area is going to be very sensitive anyway, so it's
a small die. That's the point, and a small die is always critical in power losses. So that's, for me, with the GaN devices, the most critical part. You need to be really precise with switching. When you go with silicon carbide on the totem pole, silicon carbide has a body diode effect, so it's like no-brainer there. With silicon carbide, I think when you use the Vienna bridge rectifying topology, I mean, it's proven, it's in the market, it's there for quite a while, so not expecting the big issues there. And when it comes to the motor inverter in there, I personally would stick with IGBTs, and that's mostly due to the long lifetime that is needed by the compressor, by the motor of it, because when you switch quite fast, you stress the motor inductor windings, the wire-to-wire insulation, and to make this more kind of proof for faster switching, you need different coating, you need to test the coating and stuff, and you need to stress the coating, you need to be fully aware about what's going on.
And it's just, and again, this comes back to the question of switching as well. So if you were to use silicon carbide in an application like that with the compressor motor, even if it's still working at AC, would the switching frequency be the same as the phase frequency coming into that? Would it be?
No. The switching frequency would be,
like, we're talking kilohertz, aren't we?
20 to 60 kilohertz, depending on
and as a result, that's going to make a completely different magnetic environment for those coils, vibrating around, all that, and that's why you have that issue.
Yeah, and that's why I'm a little bit the conservative engineer. I'm fully aware of that, but if you want to ensure really long lifetime, it's probably best to stick with IGBTs, and you don't lose that much. So
I think it's also fair to say that IGBTs have had such their history is so much longer and so much more proven in those applications. So whereas I would say silicon carbide's had not as long on the market compared to IGBTs. So
yes, I mean the first IGBTs that in the 80s.
So it's a long time they've been around.
It's a long time. Silicon carbide is already 20 years-ish.
Oh, blimey.
So,
it's actually quite old. It's not already... okay, so it's been around for a while. But I think it would be fair to say that it's only really been recently where they've really kind of exploded in the market.
Yes.
In the same way, like, they're just everyone's talking about it now. But actually, that's a good question. Why has it taken so long for them to sort of gain this amount of attention and attraction?
I think that was down to the ability to produce this thing in masses, because producing a silicon carbide wafer is way different to what silicon wafer production looks like. I mean, silicon wafers, it's like
you have a little C crystal in, it rotates, and it comes out.
Yes,
of course.
Not the case for silicon carbide.
Oh, really? How do you?
For silicon carbide, you have a source wafer, and you glue it to the top of a chamber. And beneath that, there's silicon carbide boiling. And
is it chemical? Oh, physical vapor deposition.
Yes.
Physical vapor deposition.
Yes.
Oh, right. I didn't realize that they're actually thin film coated.
And the thing is, silicon carbide misses the liquid state. So it's either solid or just gas. And that's the point. So the thing is to just get this a stable process. You always get byproducts, and then if you have in your source wafer somewhere a defect, it kind of grows
and goes around. Oh, that's really interesting, because I suppose that you'd have to, first things first, you need to have a source of silicon carbide that's pure in its own right, and I'm sure there are other ways of sort of growing that, but you need it in a wafer form. So you need to get a pure ingot that you not melt down, but you sort of like heat up to the point where it starts boiling inside this chamber, which I imagine will be a vacuum chamber, shooting off the silicon carbide. Hang on a minute. If silicon carbide boils, does it come off as silicon carbide, or would it come off as its constituent parts, as individual silicon and carbon atoms?
No, it boils as a whole.
As a whole, so you'd have the actual silicon carbide structures, and then they essentially thin film onto the.
They just grow very slowly, and with silicon we're talking meters per hour, and with silicon carbide I think it's millimeters per hour.
Oh, well, that's crazy. So it's expensive, takes a long time, may not work, defects are more problematic.
Yes, and then you need to saw this tiny potato that's coming out of it, and for I think the number is 1,500 kilometers, you need to have a steel wire, a diamond steel wire, 1,500 kilometers to saw that thing.
Hold up. So you take the die itself, and then you're growing the you take the source wafer. Which itself is probably, I imagine, just a silicon wafer, is it? Or is
it's silicon carbide. It has to be silicon carbide.
Oh, so you have so who made the first silicon carbide wafer?
It was just growing.
So they just grew. So they grew this one specifically in a very controlled condition, not in the same way you would with the ingots that you would do for silicon wafers. And then you slice it after it's grown.
Yeah.
Oh, blimey! So you really have to Oh, blimey! That's a really involved process, because, like you say, normally you can just grow them out if it's silicon, but you've got to
then you have a saw that just cuts it, and you. I mean, it's very bluntly said, you not just cut it.
And that's why that one small defect becomes a seriously issue, because it's not like a normal wafer that you draw out. You have a defect there, it won't be here, but there it's like that defect's going to propagate down the whole length. Oh, that's really interesting.
And the source ingots are just like.
They're only about that thick afterwards.
Yeah.
That's crazy.
And that's the point. And the first starts with like 4-inch wafer, and imagine the early silicon carbide transistors being like 9 millimeters by 11 millimeters, somewhere there. So imagine how many transistors you get out there, and if you have defects, you get even less. And then there were the 6-inch ones, and it's still, if you're not in a good position, and lots of these semiconductor manufacturers for a very long time were stuck at a 35% yield something, and 35% yield, looking at what efforts you have to kind of produce that just to get to the wafer itself, it's horrible.
That's absolutely crazy. And all of this comes back down to the heat pumps, which comes down to the issue of why it's expensive to integrate them, why they've taken so long to become popular, and And so even though we've got these silicon carbide devices, now that they can be used in the heat pumps, we've still got many challenges with using them, like the gate drivers, for example. So in terms of integrating these devices into heat pumps, compared to IGBTs and other and standard silicon devices, how much harder would you say it would be for an engineer to sort of change their design to use these new technologies?
I would say it's a learning process of half a year to a year to just. I always, when it comes to new technologies, I urge the customers and the R&D departments, please make a test project where you don't have a fixed deadline, where
it's
you
just
can fail.
Used.
Yeah, you need something where you can fail and learn. And engineering is always about building something, testing it till it breaks, and then optimize it further on.
Of course.
And that's what I always urge the engineers, like, please, if you go into a new technology, just try yourself, play around with it, and you don't need to purchase any samples or whatever, because we can give them samples to just test and break. And
now that is exactly what I was about to ask you. I was going to say, if engineers are out there, need samples, or they want to try something new, especially with evaluation kits, is that something that Avnet Silica can provide?
Yes.
Fantastic.
For the samples, it's more an easy thing. For the evaluation kits, it always depends which one, because the bigger the evaluation kit is, the rarer they are built. So it can be that on a supplier website, there is a eval kit that's like 15 kilowatts PFC whatsoever. It's not something they have on stock in like hundreds of pieces. Mostly for them, it's like, okay, we give the information out there, how we did our kit, and they mostly use it in their own labs to test their own devices. So what we always can do is get them schematics, Gerber files, firmware, if it's something that's digital controlled, but the actual hardware is more difficult to get because we need to extra produce it.
But that could also, but you could provide design references and stuff, so
yes.
like how to use that part in that circuit,
Yes.
the components you need, and that's great. So obviously heat pumps are going to be a massive thing in residential, and also commercial. But do you also think that they might play a role in things like data centers as well?
For climate control things, yes. Just for data centers, they produce heat themselves anyway.
Yeah.
So you just need.
But you need to extract it out, and that's
Yes.
and so essentially heat pump in that direction is essentially an overglorified air conditioner essentially.
Essentially, yes.
Yeah.
You always need to kind of make the case up front properly what energy is needed when.
Yeah.
During summer, obviously cooling. During winter, maybe heating. But in data centers,
It's always cooling essentially. Yes, it's always cooling because it's always hot, and so yeah. But in that situation, do you think there could ever be applications whereby the heat from those places is drawn out? But then I suppose you would then pump that heat directly into people's homes if you were going to sort of use that, or would you then have some sort of heat exchanger to try and pull it out, which then comes into another application for heat pumps to try and efficiently pull it out?
Theoretically, it's possible, yes, but you need to have the data center in some vicinity to
the residential area. So again, unless you're living right next to it, it's not going to be of any use anyway. That does actually make sense, to be fair, because I think there are places, I think maybe in Iceland or Greenland, I'm not quite sure where they wanted to build these things near residential areas so they could pump the heat in. But like you say, actually to be fair though, silicon carbide and these new technologies could be used in the air conditioning systems that those sites will also be planning. Those sites require. Because I do believe it's still a pump, it's still a compressor, yes. It's still a evaporative cooler, and all the same components, just in one specific direction, I suppose.
Yes.
So do you think that could also be another application for it?
Yes, definitely.
And in terms of energy efficiency, do you think that could be something that they might find potentially useful in terms of the energy savings?
It depends how much it is compared to what the data center uses. So if the data center has a constant power load to the grid, like 40 kilowatts, I don't care about additional 2 or 1.99. So the efficiency is not really a.
And so, do you think that heat pumps tend to be more efficient, or like you get your best bang for your buck for smaller applications like your residential areas?
Residential areas, supermarkets, these kind of things.
So communal areas where involves people.
It always depends what kind of the building inherits. If it's a data center which draws already big power, you might not really care about the last bit of efficiency in the heat pump.
You're more interested in the efficiency of something like the actual individual machines themselves, which are, you know, that does, to be fair, that does actually make sense. And so I suppose, just sort of before we get to the end of this video, I think, where do you see heat pumps going in the future, and where do you see Avnet Silica being positioned in that market?
I think heat pumps, in the past, heat pumps were like more the dumb thing that switches on and off and produces heat on the other side and then supplies a house or bigger building. With all the new technologies, not only on the power side, they will evolve. So a heat pump can be very efficient thanks to wide bandgap materials and like proven IGBT technology. But also there is communications, there's cloud, there's like interfacing through the PV inverter and managing the energy kind of exchange between the solar systems and the heat pump, and you can do some kind of smart, I don't know, artificial intelligence algorithm where it's like, okay, in the last years you needed this much power when this temperature was outdoors, and then I plan for that with the PV system, the PV home battery, and what sort of...
And when we get that smart system, that's where these silicon devices are going to become even more important.
Yes.
Yeah. And would you say that specifically silicon carbide and GaN are going to empower that, or do you think it's more of a case of just electronics in general and the electrification of things is just what's going to provide that smart
Yes, it's basically electrification of everything that kind of leads to that route. And at the end, the whole system just needs to be designed in a way that it creates comfort for the end user, and that's the key thing.
Fantastic. So just before we wrap up this video, I've got one more question for you, which is that for those who are watching this video, if they are designing a heat pump and they want to explore these new solutions, what would you recommend that they do?
Contact us
Contact
on
Avnet Silica.
the website, find us on LinkedIn, whatsoever. Just contact us and have a conversation with us.
Fantastic. Sounds great. Thank you ever so much for taking the time to see us today.
Okay.
Thank you.